Okay, let's try and see how much energy our hypothetical fan-powered flying car would actually use. So the idea is that each of these fans sucks in air and blows it down at some high speed. And because it's pushing air down, it's applying a force to the air air applies an equal and opposite force to the car and keeps it in the air. Right, so how much force does it need to accelerate air down? Let's assume the air leaves at a velocity v. Let's consider a time interval t. How much air are you pushing down in time t? Now we know that force equals mass times acceleration, Newton's law. So if we're pushing a mass m in a time t, the acceleration of that mass is, of course, acceleration is defined as the rate of change of velocity. So the acceleration is going to be the velocity, which goes from 0 to v, divided by the time. So the force is going to be mv over t, which I'm going to rewrite as m over t times v. Just moving the t for over there. The reason I'm writing it like that is m over t is the mass pushed down per unit time, which is a useful thing to know. So the force from this whole procedure is going to be the mass per unit time times the velocity. So that's right away telling us that to get a given force to hold a car up, one could go with pushing a large amount of mass down at a small velocity or a small amount of mass at a large velocity. Okay, so how much air can we actually feasibly blow down? Well, all the air blowing down you can imagine as a cylinder from each fan. It won't go straight down like this, it'll spread out, but that's going to give us a good approximation. So if we consider a cylinder like this, the area of the bottom of the cylinder is A. Let's assume we have 1 square meter for each of these fans. And the height of all the air that's blown out in a unit time is just going to be V times T. So if the air is going at 3 meters per second and you go for 3 seconds, that air will have gone 3 times 3, i.e. 9 meters down. So this cylinder will represent all the air that's been blown through the fan in our time t. Okay, so we can therefore work out what the mass, or precisely the mass per unit time is. So the mass in a time t is going to be the volume. And the volume for a cylinder like this is the area times the length, which so the volume is A VT times the density of air, which is about 1. So that's the mass. The mass per unit time, therefore, is just T cancels A V rho. So the total force from each of the 4 fans is going to be m over T V, which is going to be A rho. We've got a V from here and a V in there, so it's going to be V squared. Okay, so that's our equation for the amount of force that each fan produces. The total force is going to be 4 times that. And that's got to be equal to the weight of the car times g, if the car is going to stay in the air. As usual, we need to balance forces. Okay, so we can therefore work out what sort of speed we're going to need. So if we have that A rho V squared equals m car g, I will put a 4 in here because we're going to have 4 fans. So we'll end up that V equals root m car g over 4 rho A. If we have an A of 1.1, that comes out as about 50 meters per second, which is very fast indeed. Okay, so for this to work, we have to blow the air down very fast. The reason being we're only blowing 4 square meters worth of air. Air doesn't weigh very much, so we're going to need to push a lot of air down to keep our car in the air. You could tinker with this number a bit if you assume the car is a bit, we're assuming here that the mass of the car is about 1500 kilograms as before. If the car was a very lightweight one, you get away with less, but it's not going to be very different from this. So now how much energy does this involve? Well, the energy of the gas being blown down is just a half mass of the gas v squared, a normal equation for kinetic energy. So we've got the velocity of 50 meters per second. What's the mass? The mass is, get this from up here, so an area, so it's 4 times the area of 1. We'll do it per unit time, so a velocity of 50 times the density, which is about 1, so it's about 200 kilograms per second. So you factor 200 kilograms in here, that's about a half times 200 times 50 squared, which is about 2.5 by 10 to the 5 joules per second. Now remember, this is per second because we had our mass per unit time. So that's actually a power, that's in watts. So that's quite a lot, 250,000 watts to keep this thing in the air. So how much energy is it going to need if you're going all the way to Sydney? This is the power per unit seconds. So if you want to work out the total power to stay in the air all the way to Sydney, we're going to have to multiply by the number of seconds. If we're going at of order 100 kilometers an hour, we're going to have to stay in the air for 3 hours. So the number of seconds is going to be 3 times 60 minutes in an hour times 60 seconds in a minute times this. And we turn out the total energy is equal to around 2.5 by 10 to the 9 joules. Oh dear. Remember, our car on the ground was taking about 10 to the 8 joules, so this is taking about 10 times more energy to get it to Sydney, just to hold it in the air, than our normal car, which sounds a bit scary.